So in this video, I consider algebra of integrable functions. Algebra of integrable functions means if f and g are two bounded and integrable functions, then f plus g is integrable. Sum of two integrable functions is integrable. Difference f minus g is integrable. F into g is integrable. F by g is also integrable. First theorem is if f and g are two functions which are bounded and integrable, then f plus g is also bounded and integrable. Now to prove this, in all the four theorems, we use one important result. We state and prove that as a lemma. And lemma states like this. The oscillation of a bounded function f is or f of x is the supremum of the set of numbers f of alpha minus f of beta such that alpha beta belongs to AB. This is a lemma. First you have to understand this one because we use in all the four theorems we use this result. What does result state? Oscillation of a bounded function. What do you mean by oscillation? Suppose capital M and small m are the bounds of fx, upper bound and lower bound of function fx in an interval AB, then the oscillation means m minus m. M minus m is oscillation of f in AB, in entire interval AB. Then this m minus m is supremum of this set of numbers. Mod f of alpha minus f of beta, where alpha beta belongs to AB. What do you mean by supremum? Supremum means suppose fx is any function. We say that m is supremum of fx if m is greater than or equal to fx. That means m is upper bound. Supremum means it is the least of all the upper bounds. M is the upper bound of fx, means fx less than or equal to m for all x, and m minus epsilon is not an upper bound, is less than fx for some x belongs to AB. That is the meaning of supremum. What does lemma states? Capital M minus m is the supremum of this number, set of numbers, f of alpha minus f of beta, mod f of alpha minus f of beta. Now first we prove this. I think you followed this idea. What is the meaning of supremum? Supremum means least upper bound, and you have to prove that m minus m is the upper bound of this set f of alpha minus f of beta, and m minus epsilon is not an upper bound. M minus m is upper bound of f of alpha minus f of beta. That means m minus f of alpha minus f of beta less than or equal to m minus m. But there exists alpha 1 beta 1 belongs to AB, so that this f of alpha 1 minus f of beta 1 mod is greater than m minus epsilon. First condition gives m minus m is the supremum, upper bound. Second condition gives that is m minus epsilon is less than f of alpha 1 minus f of beta 1 gives m minus m is supremum of this set of numbers. Now I explain the detailed proof of this one. Proof is like this. Proof of lemma first. Let capital M and M be the bounds of be the bounds of fx in AB. Fx is bounded here. Then what do you mean by m and m are bounds? M is the upper bound, small m is the lower bound. Then there exists alpha beta belongs to AB, so that m is less than or equal to f of alpha, less than or equal to, or I write f of alpha comma f of beta less than or equal to capital M. Understand this first. Capital M is the upper bound. Therefore, for all alpha beta belongs to AB, capital M is greater than or equal to f of alpha and f of beta. Small m is the lower bound. Therefore, for all alpha beta belongs to AB, small m is less than or equal to f of alpha and f of beta. Now from this we can write f of alpha minus f of beta. I take mod. Why you have to take mod? Because there is no restriction of f of alpha and f of beta. F of beta may be less than f of alpha also. Therefore, mod f of alpha minus f of beta is less than or equal to m minus m. Take this as 1. What does this imply? M minus m means oscillation of fx. Oscillation of fx is the upper bound of these numbers, f of alpha minus f of beta. This gives, one gives m minus m is oscillation of fx is upper bound. But we have to prove that least upper bound. That is the least upper bound. For that we use this one. What is given? Capital M is the upper bound of fx in AB. D means this is the supremum of fx in AB. This implies there exists alpha 1 belongs to AB such that f of alpha 1 is greater than m minus epsilon by 2. Correct? Let me verify this. M minus epsilon by 2. That is the meaning of the upper bound. The upper bound means m is the supremum of fx. Supremum means it is the least upper bound. Any number less than m is not an upper bound. That is the meaning of least upper bound. Also, small m is the lower bound of fx in AB. So this implies there exists beta 1 belongs to AB such that f of beta 1 is less than m plus epsilon by 2. What do you mean by the lower bound? The lower bound means this m is the lower bound. M is less than fx for all x belongs to AB. That is the meaning of the lower bound. Now, the lower bound means any number slightly greater than m is not a lower bound. Any number slightly greater than m plus epsilon is not a lower bound. There exists beta 1, so that f of beta 1 is less than m plus epsilon by 2. Now, from these two, we can write f of alpha 1 minus f of beta 1 is f of alpha 1 minus f of beta 1 is greater than m minus epsilon. Correct? M minus m minus epsilon. How do you write this? Say I write minus f of beta 1 is greater than, here you can write minus f of beta 1 is greater than minus m minus epsilon by 2. Then you have to add this and this. These two you have to add. F of alpha 1 minus f of beta 1 is greater than, see the sign here, greater than m minus epsilon. Now take this as 2. See 1 and 2. Therefore, mod f of alpha 1 minus f of beta 1 is greater than or equal to f of alpha 1 minus f of beta 1 greater than m minus epsilon. Take this as 2. Now, what does 1 and 2 gives? 1 and 2 gives m minus m it is the supremum least upper bound of set of numbers f of alpha minus f of beta. Therefore, m minus m means oscillation of fx, that is bounded function in a closed interval is the supremum of the set mod f of alpha minus f of beta, where alpha beta belongs to AB. This is the theorem, and we use this lemma to prove the algebra of integrable functions. I think the lemma, proof of lemma is clear to all of you. Now, using that lemma, I explain how that lemma is used. First theorem is like this. If f and g are two functions which are bounded and integrable, then f plus g is also integrable. Now, to prove this, first of all, f plus g is bounded. To prove that, since f and g are bounded, there exists k, real number k, such that fx is less than or equal to k, g of x is less than or equal to k for all x belongs to A. Now, take f plus g. F plus g is less than or equal to k plus k, that is 2k for all x belongs to A. This implies f plus g is also bounded in AB. This is the first part. F plus g is bounded. Now, to prove that f plus g is integrable, we use the previous lemma. I explained how to prove that f plus g is integrable. Now we prove that f plus g is integrable. For that, let d is equal to x0, x1, etc., xr minus 1, xr, xn minus 1, xn is equal to b, be any division of AB. And also, this is important. See, in all the theorems we use this technique, mr dash, mr dash, mr2 dash, mr2 dash, and capital mr. Three sets we have taken: mr dash, mr dash, mr2 dash, mr2 dash, capital mr, small mr. Be the bounds of f, g, and f plus g in delta. What is delta? xr minus 1, xr. They are respectively upper and lower bounds. See, the first thing is, we have taken d is the division of AB, and three sets we have taken: mr dash, 2 dash, 2 dash, mr be the bounds of f, upper bound, lower bound. 2 dash is upper bound and lower bound of g. MR, MR are upper and lower bounds of F plus G. Now, if alpha 1, alpha 2 belongs to A, alpha 1, alpha 2 belongs to not AB, we take alpha 1, alpha 2 belongs to XR minus 1, XR R subinterval. Then consider mod f of alpha 2 plus g of alpha 2 minus of f of alpha 1 plus g of alpha 1. It is equal to mod f of alpha 2 minus f of alpha 1 plus g of alpha 2 minus g of alpha 1. Correct? We can write less than or equal to mod f of alpha 2 minus f of alpha 1 plus g of alpha 2 minus g of alpha 1. Which result is yours? Mod A plus B is less than or equal to mod A plus mod B. Now, we use that lemma here. What is lemma? Lemma is the oscillation of bounded function fx is the supremum of the set f of alpha minus f of beta. See the previous lemma. Now, therefore, what is mod f of alpha 2 minus f of alpha 1? For that, take oscillation of this f in delta. What is the oscillation of f in delta? It is capital MR dash minus MR dash. What is the oscillation of g of alpha? MR2 dash minus MR2 dash. Now, therefore, capital MR minus MR is less than or equal to MR dash minus MR dash plus capital MR2 dash minus MR2 dash. Here we have used the lemma. Oscillation of bounded function f is supremum of this side. Now, this is one step here. We have proved that MR minus MR is less than or equal to this. Let epsilon be greater than 0, any p assigned number, since f and g are integrable. It is given f and g are integrable. There exists a division of AB, division D of AB, whose norm is less than or equal to delta. The corresponding oscillatory sum is less than epsilon by 2. Now see here, what is given? F and G are integrable. Therefore, by sufficient condition of integrability, oscillation of fx and gx are separately less than epsilon by 2. Therefore, we suppose that division we have assumed is such division whose norm is less than or equal to delta. Therefore, sigma mr minus mr is less than or equal to sigma mr dash minus mr dash plus sigma mr2 dash minus mr2 dash. Now, this is less than epsilon by 2 plus epsilon by 2. Here we use the oscillatory sum is, what is this oscillatory sum of fx? Oscillatory sum of gx is less than epsilon. Therefore, sigma mr minus mr is less than epsilon. There exists a division D such that the corresponding oscillatory sum of f plus g, because what is sigma mr minus mr refer that one. Mr minus Mr and Mr. What are these? Mr and Mr are upper and lower bounds of F plus G. Therefore, sigma Mr minus Mr is less than epsilon. The oscillatory sum of F plus G is also less than epsilon. Therefore, Fx is F plus G is integrable. This is the first theorem. I think all of you have followed this one. Proof of this. I explain briefly once again the proof of this. We take the three sets Mr dash, Mr dash, Mr2 dash, Mr2 dash, Mr, Mr be the bounds of F, G, F plus G. Then this lemma is important. Suppose alpha 1, alpha 2 belongs to this R subinterval. Take this F of alpha 2, G of alpha 2. Then using this inequality up to this step it is clear. In this step, which result is used? Lemma is used here. Mr dash minus Mr dash is greater than or equal to this. Mr2 dash minus Mr2 dash is oscillation of G of alpha, G of x. Therefore, it is like this. Now we take sigma on both sides, that is summation on both sides. Since both f and g are integrable, these oscillatory sum of f plus g are separately less than epsilon by 2. Therefore, oscillatory sum of f plus g is also less than epsilon. Hence, f plus g is integrable. You have to practice this. The art of writing the proof, you have to practice that one. And similarly, we prove the remaining. F minus g is integrable is exactly similar. You have to try that one. F into g is also integrable. F by g is integrable. I think time is up now because I have only 22 minutes for one video. Remaining I continue in next video.